Let's build something new today. This is what we're building, a sensor-controlled light that can be activated with motion. And once activated with motion, the brightness could be controlled with light. And of course, timeout after a certain time that motion has not been detected. So that's what we're building. Now, many of you already have something like this in your house, pretty typical night lights that can be activated via motion, and they also get brighter when it's dark and when there's a lot of light, it changes the brightness, and if I cover the sensor, as you can see, it gets really bright, and when I uncover it, it gets less bright. So I'm actually using my light strip to show the light actually getting brighter and darker, but we could have also done it with a regular dimmable light as well. We're going to see how this is built using our object-oriented method, our sensor technology, and fun Python code. So we're going to see how to integrate these two types of sensors in using our Pico library and our object-oriented design, and see how to build this thing. So let's get started. All right, so let's take a look at the design that we're going to be using for our implementation. That's always the first step. We want to take a look at the design. We will think about how to make this system work, and then we will go ahead and implement it. The Pico library already has a sensor hierarchy that is already implemented. If you are interested, I have a longer video explaining the entire sensor hierarchy that I will link from this video. But suffice to say, there is a superclass for sensor. It's got some basics like the name of the sensor, whether it's active low or active high, which means whether when the sensor is tripped, does it go low or a lower value, or does it get high or a higher value? And methods like to get the actual value from the sensor and to check whether it's tripped or not. Those are the basic things that the sensor superclass implements. In fact, there are different types of sensors. As we saw last week, the DHT sensor is kind of a digital sensor, but unlike the digital sensors that we're going to be talking about today, the DHT sensor collect temperature, humidity readings, and other things that the digital sensors that we're going to be talking about today can't do. So today we're basically going to be looking at two very basic types of sensors. The digital sensor that we're going to be looking at this week only have a high or low value. For example, this PIR sensor, it actually gives you just one of two values, well, 0 and 1, or high and low. So when motion is detected, the output of this digital sensor goes high, and when motion is not detected for a while, the output goes low. Now, of course, these digital sensors, if you look at the documentation, there are controls that you can use to basically tune down how sensitive it is, like how far it can detect motion. You can also change how long the sensor stays latched after it detects a motion. We obviously don't want to get a spike and then goes away. So those controls are directly, you have to use a screwdriver and change the potentiometer to change it. But at the end of the day, it gives you one output that is high when motion is detected, low when motion is not detected. That's it. So one of two values. As we said, the LDR, or the light-dependent resistor, is actually a resistor that changes its value depending on how much light it gets. So the more light it is, the lower the resistance. The less light it is, the resistance is high. And you can use it in series with another resistor to get the voltage between the divider, etc., to get how much voltage you're getting. So that's essentially how internally it works. But basically, since we are doing object-oriented design and most of the internal characteristics are taken care of by the library, all we need to know is how to use them. For digital sensor, we set it up and we can set it up and get the raw value, which is going to be either 1 or 0. We can check and see if it has been tripped or not. So that is if, it got essentially if it's become high for our PIR. Or I can set a handler so that the sensor tells me when the sensor got tripped or untripped. So I don't have to keep checking it. Whereas the analog sensor, you basically have to keep checking to see what the current value is. And you can set a threshold. So if you are only interested in seeing when the value becomes higher or lower than a specific threshold, then you can call tripped and it'll tell you whether it's higher or lower than the threshold. That is, if it's tripped or not. So that's essentially what we're doing. And that's what we'll be doing for our MagicLight class, which keeps an association between light strip, which is what we're going to use to display the light. I'm not putting in all the attributes and stuff for light and light strip. We have already seen that class. And we're also going to set up some settings like how long it can stay on. You saw that this guy, the one that I showed, it can stay on for about 10 seconds, but that's a parameter. And after 10 seconds, if no motion is detected, it's going to turn itself back off. And of course, also how much light it needs to see before it turns itself off. So that's the minimum brightness. And then since we are going to be using the handler, when the sensor is tripped, we do something. When the sensor is untripped, we could do something. And then how do we control the light? Those would be the methods of this sensor. So let's implement this. All right, we are in Walkway and let's create a new project. And we're going to create a Pi Pico project with Raspberry Pi Pico, MicroPython. And today, all we need is the sensor class and the light class. Of course, the sensor needs the MPU driver and the light strip needs the light, and we always need the log file. So we're going to upload those files. Okay, so these are the files that we need from the library. We need the sensors file, which has the implementation of all kinds of sensors. We need the light strip to control the light. And the sensor also uses this MPU. We're going to be talking about MPUs later on in another video. So that's all we need. Let's wire these up. We, of course, need a light strip. NeoPixel. We're not going to bother changing the number of lights. We can actually use all 16 of them today. We are going to need a PIR sensor. That's that guy, PIR motion sensor. And we are also going to need an LDR photoresistor. Now, the photoresistor in the Walkway simulator actually has both the digital output as well as the analog output. We're going to use the analog output because that's what I want to show you how it works. Let's put the sensor in the middle. Now, one thing that you should remember when working with the Raspberry Pi Pico and analog sensors is that there are only 3 pins that can be used for analog input. The Raspberry Pi Pico has 3 ADCs, or analog to digital converter, because internally the Raspberry Pi Pico only uses digital signals, right? So in order to use an analog sensor, it needs to convert. Normally, an LDR needs you to put a 10K or a high value resistor in series with it and create a voltage divider. This particular packaging already has that resistor built in, so we don't need to do anything about it. If we just want to use the analog output, we can just connect it to one of the 3 analog pins of the Pico. And so what we're going to do is let's just add a ground bus as usual. We're also going to add a VCC bus. So we can connect all of these guys to VCC and ground. So this is the AO or analog output, and as you can see, it's got a digital output as well. We're going to use the analog output, and notice that the moment we select an analog output, the simulator lights up only the 3 pins that can be used. We're going to use, let's say, pin 27 for the analog output. And here is ground. We're going to just connect it to this ground pin, VCC, we're going to connect to the 3.3 volt pin. And for this guy, the PIR does need 5 volts because it has an internal voltage regulator. So we're going to put it to the VCC bus. The ground can go to the ground pin. And the output, let's put the output to any of the input pins, so we're putting it to pin 20. And for this guy, we're going to use the ground pin here. The VCC goes there. And let's put the digital input pin to our favorite pin 2. So that's our circuit today. So pretty easy. We've got 2 sensors controlling 1 light. Now what we're going to do is build our own MagicLight class. Okay, so here's our code. Just like I showed in the design, I created a class called MagicLight, which basically has an init that takes the on time, which I set a default value of 10 seconds, or 10,000 milliseconds, and the minimum light brightness at which it will turn on. I don't want it to be on when it's moderately bright, so it needs to get to about 20,000. Remember that it's going to increase value as brightness goes down because the resistance get higher. And then we created instances of our LDR and the PIR class. Notice that LDR is just an analog sensor and the PIR class is a digital sensor. But this one has a low active of false because when a PIR gets tripped, it becomes high and not low. There are sensors when they get tripped, they get low. So we're going to use low active as false for that one. And then we'll keep track of when it was last tripped so that we can see whether it's time to turn it off or not, or keep it on for a while. And here's the control method, which is basically an infinite loop that checks the time. And if it's time to turn it on or keep it on based on the last time it spends motion, we're going to check the value from the LDR. And if the LDR value is more than the minimum light required, we're going to divide that value to set the number of LEDs. So basically divided by 65,535, which is the maximum, and multiply it by the number of LEDs so we know how many LEDs to turn on. And that's how many lights we turn on. And that's it. Otherwise, we turn it off and sleep for half a second and we continue this process. Now, if the PIR gets tripped, it sends us a handler message saying the sensor got tripped, and we just basically update the last time the sensor was tripped so that our loop can continue using it. Let's see how this works on the simulator. You have already seen it working on the real thing, so let's check this out. On the simulator, of course, even the PIR sensor is simulated, so you will see how that works. So right now the light is off. I'm gonna make sure that it is dark. So I'm gonna make it dark. And I'm gonna simulate some motion and you'll see the light turns on. And the darker it is, the more lights will be. And if I keep changing the darkness, notice that the brightness reduces. And then 10 seconds later, since there was no other motion, it turned off again. And I can simulate motion again for it to turn on, and then simulate the brightness to simulate the brightness of the environment to control the brightness of the LEDs. And it turns off when no motion is detected. And as you saw, that this is the same behavior you saw when I demonstrated the light. So that's how you implement a sensor-controlled nightlight. I hope if you have a kit, you can make your own nightlight to have next to you. And we're going to be building more fun projects going forward. Hope this was fun and useful, and I will see you at another video.